We actually presented some preliminaries on our ESA acceleration, which today is quite complete. Last year we already had most specification we must engineer for the cars. Meaning last year was like, oh, we now have some text. And GLXGS was running. So what's going on now? Well, the first thing is we still keep this process, we've got this process of trying to build a bigger and bigger community of developers around this drive, and to me that's very important. Well, as you see currently there are only first-time people working on this, so to keep the ball rolling we've got to involve new developers all the time because people come and go. So, well, we certainly try to make as much publicity for the project as possible, which means, of course, you might all know the TIMDC, which is a bi-weekly of every week or so. It's an update on the project and says, well, this last week we've done this and that. So it gets people, actually seeing what happens, other than by having to check out the Git code and try it and buy bugs. We got associated with some news sites on Reddit, one of them. We published an article on this, breaking news. Actually, it's currently available for subscribers. At the moment, we're still very focused on working through IRC, which is very convenient because it's extremely fast and it's not like email when everyone while chiming with a special practice stuff on phones and all. IRC, well, it lets us reach kind of the compromise quite quickly when it comes to technical decisions. So it's pretty convenient to use IRC. Since we're still very much in development driver, well, we've got an unspoken policy that broken code is better than no code at all, which we apply fully when we say we've got our own version support, and when we say we've got ESA support. It was not so well working as of 6 months ago, but through continuous testing and user support, actually things did not work as well as we expected. Well, we were able to fix the bug. So I think it's a very important idea that broken code is better than not having code. So, moving on to the hardware primary. So I'm going to introduce the hardware features once again. I'm going to go into a little more detail to explain what actually justifies the choices we've been made with the design. So we're covering a 10-year time frame. We say N4, which is 98. Then we're covering the N50 somehow, which is covered this year. So, if you put in perspective, for example, look at the Radiant driver, it's pretty big for the reason that we have to handle all the hardware at the same time. So, we've got, most likely we're going to have the same issues of covering all this hardware. So, hopefully there are some similarities between the cards and we can leverage some common code easily. But although there are some differences in part with your 3D handling, which I'm going to show after this slide, which incurs that we have to write the application. So, the nice feat, we've got hardware context on the card, which means we're not going to bother with a lot of the architecture that's going to be written for other cards, which actually involves storing and restoring the context in space, which is pretty complex and has to be done with the DRM all the time, in real time in the switch applications. In the NVIDIA case, we've got hardware-based context switching, so the cards will actually expose a number of command buffers. Well, each command buffer gets a timestamp, just like round-robin scheduling in an operating system. And once the timestamp is up, well, you have the context to switch down, and the state is put on the card, and you can retrieve it for a number of milliseconds. So it's quite simple, the way it works. One very nice thing, yeah?
How many conductors?
It depends on the card. If you have an MV4, so the oldest one you've got 8, you've got 16. If you go MV10, you've got 32. If you go MV6, you've got 120. Yeah. Actually, it's not, because we'll keep one for the kernel, one for 2D acceleration, maybe one for CNC debate, and then one for 3D application, which means not so many. So yeah, we're thinking of trying to do as much as we can. And even if we don't have enough, we still have this. We can actually ask the cards to go. They can text. We don't have another protect. In fact, we can control it by hand. At the moment, we're very much in development of no other 15 jealous games at the same time with TNT. We're not hitting the limits here yet. Yeah, but it's true that the hardware can actually help you as well handle the context being used for all the just at the same time. No, the MB3 system, we're not covering this because it has 8 context. We're not covering unless someone but actually the MB3 doesn't have to test the so, to sum up, how really does that happen? Well, as far as vertex testing is concerned, the old MB4 now, obviously, from MB10 you get fixed vertex response, so it used to be called TCL and be a hot fix. Today, they're actually considering not really flexible enough for extraordinary games and applications. Starting in MB20, you've got the first generation of vertex programs here, which is available, which is very nice, because it's unified, so we can pretty much shoot the same code in those two cards across screen and vertex customers concerned. On MB40, the vertex processor was upgraded, and on MB50 it was actually merged. You've got the vertex and fragment processor in a single interface. As far as texture, combining and fragment programs are concerned, it's a bit more complex over time because it goes very fast, and so the new APIs are evolving. So we've got a lot of generations, a lot of changes to the generations. As far as video capabilities is concerned, we used to have a hardware overlay until the MB30 actually online. The very first MB40 card still has the overlay. No one's got this card. Most of the MB40 cards do not feature a hardware overlay. So we pretty much have to do video arrays by using, well, the 3D engine and fragment processing is over and as far as dual head capability, it used to be extremely cost specific and vendor specific. Like the vendor would bolt his own converter and TMDS encoder becomes having saying, hey, I've got a dual head design, but it's not basic. But starting from MB17 actually, we've got a very nice, mostly unified dual head capability, which means these cards might not really get dual head, even if you see to a system. We're not really that much investing in legal, the very difficult stuff just to get. But maybe Stuart will do it one, yeah? It's pretty good. So now, we're moving on to the reverse engineering part. So, the hot tool of the moment is called MMI Trace. You might have heard about it. It originates from the nouveau project that now has a really a life of its own. What's the idea of this tool? Well, it's a tool that's aimed at tracing inside the kernel what happens. So, if you want to know what hardware registers are touched by a binary driver in your Linux kernel, you can use this tool. As a quick introduction of how it works, well, it's very simple. You've got a trap called the IO remap tool, which basically is used to map the MMI space to not just the state of the car. So we trap this code. Next, we just remove the page mapping from this area. So the next time the binary driver tries to access the area, it will trigger a page fault, as you expect in more architectures today. We map the page, we set the single instruction, and then we remove the page again. And by stepping this single instruction, we can actually, before stepping instruction, write down what resistors were set, and what push inside this resistor. So in the end, we are able to produce traces of register sets of any binary driver that is used in the Linux kernel. So you can imagine that this project's got a very wider scope than our specific tools. Yes, it's getting used because the Mad Wi-Fi, so Mad Wi-Fi guys, they have binary feeds in their Wi-Fi driver, and they are working on reverse engineering it, and they use this tool as well. Sadly, it got broken in 2.6.24 kernels, but that's because we used a hook that was not really widely used by anything else than this tool and the kernel debugger. The kernel debugger was quite good, and we didn't really follow the Linux kernel natively. But we're now aiming for mainline kernel inclusion because that basically ensures that this effect will not happen again. This also ensures that next time we want to reverse engineer a binary driver, every single user will be able to have it as a default in the distribution to have MMI trace and do reverse engineering of a piece of hardware again. So I think spreading this tool is quite interesting for us, and that's why mainline inclusion is very important. So we might be aiming at 2.6.26, but don't take my word. Next we've got Volt-Run MMT, which is a tool that tracks user space access to MMIO ranges. So it works mostly the same as MMIO trace, but it's just in user space. Obviously you can use it on the source, so you can actually reverse engineer any binary XOR user space driver. So we can do what we do in the code, so that's in user space as well. Finally, nouveau, which is the old dog. You might have heard about it. It's very basic. This is the tool that was released 2 years ago at FOSDEM. It just maps the people. The binary NVIDIA driver maps the people inside the OpenGL application space. So this renewal is just an OpenGL application. It finds the people. It sends a couple of OpenGL commands. It looks at the people changes and says, so by setting this blending mode, you get this change in the people. So it's as simple as that. If you repeat that for every single OpenGL functionality, well, you can pretty much reverse engineer the whole 3D pipeline with that. So that's the idea. And obviously, it gets regular and new tricks, which are updated OpenGL tests. So, moving on to 2D support. So where are we now? Well, we've got simple EXA acceleration for MP4 because of hardware limitations. We cannot really do much. We tried very hard, but it's a no. On NV50, it's also very simple, but that's because we lack hardware at the moment. I actually plan to change that. Yeah.
What do you mean by simple EXA?
Well, it accelerates the copy operation and the solid field operation and the uploads and downloads from memory. That's fine. So that's the level you get in Radiant or R300 chips or Radiant HD. You get this level as well. Yes.
Then if it does only solid field why not sticking to XAS? Why? What?
That's a good question. Very early on, we decided to ditch XAA because we had the two implementations at one time in the Chicago Plateau, and we looked at the two pieces of code, and one was XAA, and it was pretty big, it was pretty complex, and what was EXA, it was very small. So, of course, we get a lower performance, but we expect in the future. So, yeah, core EXA. But you're right, this is a bet on the future. We're not interested in fast. We're not directly willing to do some release. That's what that's a good question. Yeah, we didn't really want to, impose development time into something that will get thrown sooner or later. Also, the nice thing about EXA is you can accelerate X render API. So
Yeah, but it's not in there yet, so you're not using it yet.
yes, for all this we are actually doing it.
Okay, so it makes sense.
Yeah. We didn't want to have, one path that will get fast for fonts and the other not. It's getting very complex to be better. We try to take a simplicity approach, really. I think that's very important, especially when you aim for 10-year time range. So yeah, these cards, they get pretty much all the operations you're going to need for your command desktop acceleration. Of course, as we were discussing, EXA is not yet up to speed for example, the font techniques is not really as fast as we would hope. Hopefully this will be get solved quite soon for EXA, but as far as implementing the hooks is concerned, we are implementing this. So we also get a performance gauge from synchronous uploads and downloads, even though we've been lifting limitation labels for small stuff, but still get hit pretty hard on this. And this actually depends on doing a proper TTM with asynchronous transfer. So it's more of a long-term goal. So XV would add vacation of code students involved in the approval application and you work in the XV layer. So we cannot say that move faster in the binary driver as far as performance is concerned. That's done through overlapping, the upload of a frame with the rendering of the previous frame. So overlap those two stages together. It's pretty fast. And we've got another adapter on engine 30 net 40 card which gets you a better filtering. So we've got this thing's not got, it doesn't have the better speed, but it's got a better top quality. So if you want to watch movies which involve highly upscaling, it's pretty interesting as well. And the deployments match up with that here in FOSDEM board. Basically, I just listen and then I test down the transition from the slide. Very good. So another thing that's getting more and more important, and it was actually the reason nouveau started in the first place. I had begun, but it was 2.5 years ago or something, I had begun to write the BIOS function tool to just execute the BIOS. So we've got something to where there are the API talks, they've got the state and BIOS stuff. So we've got similar stuff like BIOS. So we had to implement an interpreter for this. Ours was actually based on a home booting application from the BOS driver, which had also some bits in it. And it's that for a long time, and recently was revised by Stuart here. It was found, and we knew this from the beginning, but it was found that it was getting really, really needed for proper mode setting. Especially with all the word outputs you can file and all, it's really hiding a lot of the difficulties around the mode setting stuff. So this is a very welcome addition. Hopefully to be able to cold boot the cards as well one day, not yet the case. But for example, people who do not want to have an x86 emulator in their x86 will be able to cold boot NVIDIA plus with this. So we're thinking for our PC people that include Italian people. So R and R1.2, so yeah, we support that mostly, as I said, on the cards which get nice dual LED capabilities. As I said, the older one was more difficult. We've got dynamic reconfiguration as you would expect from R and R1.2, and still there is the static firmware location issue, which means you have to pretty much put in your XOR configuration the maximum size you ever want to use, even if you have the single screen. It has to be made for the whole session, but that's not a limitation on our side. Again, it's common architecture. We might have to work this out on it. So now, moving on to the meat, the theme support. So it's really hard to get.
FOSDEM sauna. FOSDEM sauna is.
So the old DRI model, we had actually implemented an old DRI style driver, mostly to run GLXJS. It was something like 25,000 lines. And it required 25,000 lines, which is a lot of work inside the driver. Each driver actually had to implement most of the OpenGL pipeline itself, so drivers get the big things that could be factored in are not. So it was still a suboptimal. So we've got from Tenston Graphics this really nice architecture, which is called Gelium. We try to put as much in command as possible into an intermediate task. So you can pretty much have whatever graphics API you want, and you can have very simple drivers. So for a point of comparison, we used to have these 25,000 line DRI old school drivers, and now we've got a 4,000 line ND40 driver, which is working as well or even far better than the DRI1. And as far as NG10 is concerned, at the start of implementation it should be pretty complete, but doesn't work yet. Because the card is much simpler, the implementation is 2,000 lines. So we've got a mostly working 3D driver in 2,000 lines, which is great. As far as maintainability is concerned, this is my work. So you're probably going to ask that if we use a shader representation, in the middle of the pipeline, what about cards that do not have this shaders? Well, it's fairly work as well, because these cards will get some additional intermediate representation. So we've got it's just extending to all the cards. It's just as simple as adding additional instructions to the fragment and vertex program instruction set, which basically mimics the behavior of the old fixed pipeline. So you get basically passed down through the pipeline programs that are not real fragment programs, but simple things that describe these old OpenGL extensions, just using instructions. So this design can actually extend to support this old card as well, and this is work that I'm doing at the moment. And I hope to have an ND10 driver soon and be able to show this out, because I think this is still important to support older cards. And Gelium, in my opinion, is too important to be kept for fragment shader supporting only cards. So I think it's very important to extend it to all the cards as well. So our current Gelium development, the ND40 driver is somehow working. We'll have Stuart demoing afterwards, I think. Yeah? You're in for a demo. You're going to demo? One of them, actually two of them are going to demo. The ND10 and ND30 driver are under development. If you're watching the gate, you can see that I imported the ND30 driver a week ago, and I've not yet imported the ND10 driver. So what does the future hold? Well, the big one, the TTM. This is more the memory management. If it was just internal memory management, well, we would just be able to replace our API and say, well, we already have our own memory manager, so we could just switch with the TTM. But it's not as simple as that, because it will manage memory. It's also going to move the memory as other applications require. So it's now something the application uses in video memory is moving. Well, the application has to know somehow. So that's the work involved. It's not really possible to have the application really know. So the solution is another one. It's that the application passes its common buffers to the kernel and tells the kernel where the offsets actually live. And the kernel will do what we call relocating or offset fix-up. It will override the offsets with the proper offsets for each resource. So since the kernel knows it has to do the work. To achieve this, there is something called super IOCTL. It's not that super in our case. Other drivers do a lot more than we do in this. But we're going to have this as well. So we're going to have to implement this. So CTL is not really easy, especially since there's users has to notice the kernel that in the command buffer, so you've got a big command buffer, it has to say there, and there, you have offsets which need to be fixed, obviously, by the kernel, because you're the only one who knows where one piece of memory is at one given time. So this is the job of the super ROCTL, among other things, of course, but in our case, this is mostly the job. Well, the DRI2, it's still very much in the air because for us, I mean, not in general, it's been pushed, but for us, it's still very much in the air. But hopefully, it should be an easy one because it's got a couple of purposes which we actually never had these issues. We're trying to remove the big lock, which is a lock that was, preventing application for simultaneously accessing graphics card from user space, which was quite killing the performance when you start to have lots of OpenG and stuff at the same time. It's also trying to remove the shared area. So in the old design, the kernel, the X server and the DRI applications, the 3D applications, they used to have a single piece of memory, which was shared. They could write a bit there and say, hey, I'm doing this and I'm putting this and this place. No. This was particularly useful for what we call clip rectangles, which is a major thing because when you actually do 3D acceleration in your X server, you basically have the 3D application handling a 2D buffer, which is a picture of the 3D rendering of your favorite game. But then, you all know that other windows might hide, might obfuscate parts of this 3D window. And if the DRI application doesn't know, it will copy and it will overwrite even the rest. So that's the major issue, and that's why DRI2 is there, because you've all seen this piece demo where the cube moves, but the GLSG stops with the cube surface. This is really difficult one, yeah?
For our later to DRI2 will have only one render manager.
Yeah. Well, in our case, it's very driver specific. In our case, we're not really sure. That's why I said it's still
only my understanding.
Yeah. Well, actually, you can have DRI2 and keep locking mechanism. It's not explicitly prevented, but the new design lets you have a lockless. It lets you have a shared area that it lets you do things, but it doesn't force you. It's really the same for the shared buffer. You might keep it as well if you need them. No, the design does not prevent this, but it helps you. Actually, the old design prevents you. This design doesn't prevent. That's the idea. It keeps flexible and as I said.
We don't have clear things are of the DRI2, sort of. Because the old DRI suspended on driver form exactly like that. You are out of the like that.
Yes, mostly lucky.
So sort of half of the DRI2.
Yeah, we don't know yet. There's just additional stuff with the swap buffer thing. We don't know yet which, we've got three components, kernel components, user space components, and the 3D DRI component. We're not sure where the swap buffer coupling should happen and also. We're still evaluating possibilities because there's a very big performance impact to doing this choice. So we're doing very carefully this stuff. Kernel mode setting, everyone talks about this. Jerome is going to discuss this tomorrow. How are we doing this in Radiance? We want to do this on NVIDIA. First of all, we need to stabilize our R&R 1.2 interface in user space. Obviously, debugging stuff in user space is easy. Debugging stuff in kernel space is not so much. But then, when it is stable, we plan to move it in the kernel. Except, this involves having the BIOS parsing as well inside the kernel. This is going to be a first. I think it might work actually. So that's when we do. This is very much a work in progress. It depends on a lot of things. This is why today it's not really happening. If you want to do proper satisfying and resume, you do it all from the kernel, which means that all user space components have to become pretty dumb about the card states and what they expect from the card review. As soon as we're there, we'll be able to very easily suspend and resume, but for now, fully working BIOS parser would be a nice clear because better with kernel master here. And then we have to save and restore There have been experiments. It seems to work somehow.
Not
You see, yeah.
It's very hard to do it. It will take.
Hopefully the
needs
moving
lots
more
of-
components inside the kernel will help us, because otherwise we just, if we do not move enough stuff inside the kernel, really the kernel can be the only entity knowing and having full access and understanding of the card. If multiple entities are involved to access the same piece of hardware, system information is becoming very quickly very complex. That's good. So, another question we get asked a lot about pretty much very often. We change our mind most immediately. Really, well, doing a real release and merging into mainline kernel, mainly merging the DRM into mainline kernel will require that we stabilize our API with the DRM, which is going to change because our kernel got set. So it's also going to change because of the TTM and super IO CTM. So this is still one of the pending issues that depend on other stuff and this kind of things, much like suspended regime. We might get those two at the same time because those actually have the same requirements. So we could, of course, we could decide to stabilize on the current interface, but then we get by the Linux policy to maintain this interface forever. So not good. It's not really in our own interest. At the moment, we want to